Welcome to this explainer. Let's jump right into it. Today, we're embarking on a pretty fascinating journey, taking basic coding concepts and transforming them into a master blueprint for building highly adaptable, super robust software. If you've ever felt like your code was getting a bit too rigid or maybe just disorganized, you are absolutely in the right place. We're going to unpack advanced Java architecture and see how we can turn raw syntax into the structural foundation of an entire digital city. Okay, let's dive into our roadmap for today. First, we'll cover class blueprints and basics, then memory and static sharing. Third is polymorphism. Fourth, we'll look at abstraction and interfaces. And finally, we'll wrap up with generics. We're going to build our knowledge progressively here. All right, Section 1, Class Blueprints and Basics, the foundation. Every great architecture starts right here. So at its core, what is a class? Well, it's really just a blueprint. You can think of it like a cookie cutter that we use to stamp out objects that model real-world things. Actually, let's frame this in everyday language. Think of the class itself as a noun, like a person. The properties, things like age or name, are the adjectives describing that person. And the methods, like talking or walking, well, those are your verbs. When you think about it, writing code is really just building sentences. Now, with those nouns defined, we get to decide how they interact. When we architect systems, classes usually communicate in two main ways. First up is inheritance, which is an is-a relationship. For example, a student is a person. They automatically inherit all those human traits from their parent class. The second way is composition. This is a has-a relationship. Think of a teacher who has a student in their classroom. The teacher doesn't inherit the student's traits. They simply utilize that other class to get things done. Once you have your blueprint, you have to decide who actually gets to see it. That's encapsulation. If you mark a property as private, only the class itself can see it. If it's public, literally anyone can access it. But there's this fantastic middle ground called protected. This is an awesome tool because it keeps the data hidden from the outside world, but allows the class itself, and crucially, any of its subclasses, to easily use it. And before we move on from the basics, we absolutely have to remember the ultimate parent class. In Java, every single class automatically inherits from the built-in object class. Because of this, there are three essential methods we should really get in the habit of overriding in our blueprints. Equals, to determine if two objects are truly the exact same, toString, to give us a nice, readable text version of our object, and clone, to safely duplicate it in memory. Moving right along to Section 2, Memory and Static Sharing, the infrastructure. Let's look under the hood at how the computer manages these blueprints. It's super easy to think of variables and data structures as just abstract concepts floating around in the ether, but they are highly physical. Data structures are simply a system of memory management. Just picture a computer memory as a giant physical wall of numbered mailboxes. When you create an object or an array, the computer is literally just reserving a block of those mailboxes and keeping track of the starting address so it can find your data later. Now, what's really interesting is how we can manipulate that memory for incredible efficiency using the static keyword. When you make a variable or a method static, you're telling the computer that this specific piece of data does not belong to any individual object. Instead, it belongs globally to the class itself. It's shared across every single object spawned from that blueprint. The magic number to remember here is 1. Because the static data structure belongs to the class, memory for it is allocated exactly one time when the application loads. Imagine you're keeping account of the total number of students enrolled. You really don't want every single student object holding its own individual disconnected counter. By making the total counter static, all those student objects look at the exact same single mailbox in memory. It's a brilliantly efficient setup. All right, Section 3, Polymorphism. Code that adapts. Let's see how our code becomes a shapeshifter. Polymorphism. It sounds like a heavy academic term, but it actually has its roots in biology. It comes from the Greek words polis, meaning many, and morphe, meaning form. And just as an organism can take on different forms, our code can too. In object-oriented programming, this happens when a parent class reference is used to refer to a child class object. It allows our architecture to be incredibly dynamically flexible. So the crucial point here is that polymorphism lets us write flexible methods that effortlessly accept any related child object. Imagine you're writing code for a meeting. Instead of writing separate, tedious code to accept a doctor, and then a student, and then a teacher, you just tell the meeting to accept the parent class person. The meeting code dynamically adapts to whatever specific type of person walks through the door.
And hey, if the meeting ever needs to know exactly who just walked in, it can evaluate them on the fly using the instance of operator. Let's shift gears a bit. Section 4, Abstraction and Interfaces, the Rule Maker Celeste. Building a massive digital city requires strict contracts, and this brings us to abstraction. This is the quality of dealing with pure ideas. It focuses entirely on what an object does, completely hiding how it does it. Think about food for a second. You can't just sit down and eat a generic, abstract food class. Food is just an idea. To actually eat, you have to instantiate a concrete subclass. You have to eat a donut or a banana. Abstraction lets us program the general idea of eating while leaving all the messy details to the specific item. We usually pull this off using two main tools, and it's vital to know the difference. Both abstract classes and interfaces cannot be instantiated directly, but an abstract class is kind of like a hybrid. It can mix abstract ideas with actual concrete coded methods. An interface, on the other hand, is entirely abstract. It contains no code bodies whatsoever. It acts strictly as a set of rules, a rock-solid contract that any participating class absolutely must agree to follow. Setting up one of these contracts takes 3 pretty simple steps in practice. First, you declare it using the interface keyword instead of class. Second, you define only the method signatures, so just the names, return types, and parameters, and you end it with a semicolon. No curly braces, no code. Finally, any class that wants to play by these rules uses the implements keyword. That guarantees it will provide the actual functional code for every single method listed in that interface. And that brings us to our final stage, Section 5, Generics, the universal tool. The word generic basically refers to a characteristic of a group that isn't specific. In Java, generics are denoted by angle brackets, usually with a capital T inside. This T acts as a brilliant little placeholder for a data type that we're going to define later. Why do we do this? Simple. It saves us from having to write the exact same method dozens of times, just to handle different data types like strings, integers, or our own custom objects. It literally translates to the ultimate write once, run with anything paradigm. If we translate the raw Java syntax, think of a generic class as a magical box. If you code a generic box with a T, you're building a container that perfectly shapes itself to whatever you put inside. The very moment you instantiate it, it can instantly become a box specifically for strings, or a box specifically for integers, and you're doing all of that using the exact same underlying blueprint. To wield this power effectively, there are a few rules to keep in mind. First, generics use that T placeholder for dynamic class types, which means they only work with objects and wrapper classes like the capital I integer. They don't work with primitive types like lowercase int. Second, if you want to keep your magical box from just accepting literally anything, you can bound it using the extends keyword, restricting it to specific subclasses. And finally, as a super nice quality of life update, newer Java versions allow you to use the empty diamond syntax when you instantiate. It saves you some typing while maximizing both your code reuse and your memory efficiency. Wow, we've covered incredible ground today. From the foundational blueprints of classes and encapsulation, navigating the physical memory of static elements, to designing adaptable, shape-shifting code with polymorphism, enforcing strict rules with interfaces, and finally, forging the ultimate universal tool with generics. The pieces are all on the table for you. So, I leave you with this question. Now that you have the blueprints, the memory maps, and the universal tools, how will you architect your next digital city? Thanks so much for joining me on this explainer, and happy coding.